Hello students, welcome to Spectra Education Academy. In this video, I am going to explain answers for previous NEET questions from the chapter Potential and Capacitance. First question is, the parallel plate capacitor of area capital A, plate separation D and the capacitance C is filled with 4 dielectric materials having dielectric constants K1, K2, K3 and K4 as shown in the figure. If a single dielectric material is to be used to have the same capacitance C in this capacitor, then its dielectric constant K is given by. So this is given 2016. Now let us continue with the answer. Remember, when the areas are divided. So first let us write when areas are divided. So assume that capacitors are in parallel combination. Before we write the effective capacitance in parallel combination, let us write individual capacitances when they are filled with dielectrics. So K1, this is filled with A by 3 epsilon naught. The separation is D by 2. So you can further simplify this. K1 A epsilon naught, 2 will come up, D get multiplied with 3. Similarly, C2 is equal to 2K2 A epsilon naught with 3D and C3 is 2K3 A epsilon naught with 3D. So remember, areas are divided, so they are parallel. So therefore, C effective parallel is equal to C1 plus C2 plus C3. So you are adding, that means you can directly take out common 2A epsilon naught, 3D you can take out common. So this is multiplied with K1 plus K2 plus K3. Now let us also write capacitance for the dielectric constant filled K4. So what is that? So this is filled with complete area. So therefore, there is no division in the area. So it is K4 A epsilon naught, but the separation is D by 2. So 2 will come up, D will be at the denominator. Now C4 and the C effective are in series because the distance is divided. So get back, C effective series is equal to 1 by C effective plus 1 by C4. So what is C effective parallel? This is C effective parallel 1 by. So therefore, if you simplify properly, 3D will come up. 2A epsilon naught will be at the denominator. K1 plus K2 plus K3 plus, even for C4 also, D will come up. The denominator will be 2K4 A epsilon. Now 1 by C effective. C effective can be written as K effective A epsilon naught. D will come up. So therefore, this is 3D. 2A epsilon naught. K1 plus K2 plus K3 plus D by 2K4 A epsilon naught. So A epsilon naught, both the sides get cancelled. And D get cancelled. So therefore, you can take here 2 common and you can take this up. So therefore, 2 by K is equal to 3 by K1 plus K2 plus K3 plus, this is going to be 1 by K4. So let us check which option is correct. So 2 by K is 3 by K1 plus K2 plus K3 with 1 by K4. So fourth option is correct. Now moving to the solution of question number 2. A capacitor is charged by a battery. The battery is removed. So when it is charged, there is energy stored. It is CV square. Battery is removed and another identical uncharged capacitor is connected in parallel. So therefore, when uncharged capacitor is connected in parallel, so there will be common potential. So get back formula for common potential when capacitors are rearranged in parallel. C2 V2, C1 plus C2. But uncharged means V2 0. So you'll get that V common is equal to C, capacitance is C only, so therefore CV by, this is C plus C, identical only, so therefore 2C. So the new potential V common is V by 2 now. The electrostatic energy resulting system, when uncharged capacitor is connected in parallel, so what is the electrostatic energy of the resulting system? Therefore, when they are connected, you call this is U2. When they are connected in parallel, C1 plus C2, but there will be common potential. So since they are identical, so this is 2C. The C is C1, both C1 and C2 are equal to C only. So therefore, this is V common is V by 2, but there is squaring here. So this is V square by 4. So 2 get cancelled. So otherwise you can cancel this one. So therefore, if you divide, so U2 by U1 is equal to, what is U2? U2 is CV square by 2 into 2, that is U2. U1 is CV square by 2 1. So CV square get cancelled, 1, 2 get cancelled, it will be 1 by 2. So the final answer is U2 is equal to U1 by 4. So therefore, new capacitance decreases by a factor of 2. First option is correct. Moving to the next question. The diagram below shows regions of equipotential. The positive charge is moved from A to B in each diagram. So then, which option is correct? So remember, these are all equipotential surfaces. So this straight line, along this straight line, potential at every point is 10 volts only. Similarly, along this straight line, potential at every point 2 volts only. So this is individually an equipotential surface. Similarly, 30 at every point, similarly 40. So in the second diagram also, so along this curved path, everywhere 10 volts only. So similarly in the other cases, along this curved path, 10 volts only. So these are all equipotential surfaces. Remember, when charge is moved from one equipotential surface to the other equipotential surface, in all the cases, the potential difference is 10 to 40. So how much is the potential difference? 40 minus 10. So potential difference is 30 volts only in all the cases. Even similarly in the second diagram, 10, A at 10 volts and B at 40. So difference is 30. Even similarly in diagram 3, A at 10 and B at 40. So therefore again 30. In the last also. So therefore potential difference between A to B is 30 volts. So therefore it is equipotential surface. So work done in all the cases is same. So work done to move charge, because potential difference is included with the work done in moving a unit positive charge from infinity. Okay, when you talk about potential difference between one point to another point, when you talk about potential, it is from infinity work done to move an unit positive charge from infinity to a given point in the electric field is potential. So since this is same in all the cases, so work done is also same, because you are moving the same charge. So first option is correct. Moving to question number 4. The electrostatic force between the metal plates of an isolated parallel plate capacitor C having a charge Q and an area A is. Yeah, so get back the force in association with electric field intensity, that is Q into capital E. So for the metal plate, electric field intensity from the idea of Gauss law is sigma by 2 epsilon naught. So once again, Q by 2 epsilon naught, sigma is surface charge density, that is Q by area. So it will be Q square by 2a epsilon naught. So therefore, there is nowhere distance is included in the formula. So therefore, it is independent of the distance between the plates. Now moving to next question. Question number 5. So this is given in 20 NEET. In a certain region of space with a volume 0.2 cubic meter, the electric potential is found to be 5 volts throughout. The magnitude of electric field in this region. So therefore, this might be some volume. Electrostatic potential is found throughout. So therefore, if you imagine this is like a spherical shell, in case if there is no charge inside, so there is no question of existence of electric field. So there is a chance electric field to be zero when potential is constant. So that is possible in the case of spherical shell, this conducting spherical shell. So you cannot, if you construct Gaussian surface, if you want to construct, there must be charge. So therefore, there is no charge inside. So constant potential may be possible, but field does not exist. So first option is correct. Moving to the question number 6. A short electric dipole has a dipole moment of, so this is dipole moment, 16 into 10 to the power of -9 coulomb meter. The electric potential due to the dipole at a point at a distance of 0.6 meter from the center of the dipole, situated on a line making an angle 60 with the dipole axis. So what we need to find out is potential we need to find out. So get back the formula. It is 1 by 4 pi epsilon naught. Potential due to a dipole is P with cos theta divided by R square. So you remember 1 by 4 pi epsilon naught is 10 to the power of 9 and dipole moment is 16 into 10 to the power of -9. So it is cos 60, it is 1 by 2 divided by distance. Distance is 0.661, but there is a squaring. So it is 0.36. Yes, you simplify this. This is 8 times. Then, so this is going to be, if you make this as 36 into 10 to the power of -2, then this is 4 times. This is 2 times. Then there is -2 here. So there is a -9 here. So it will be -7. So this is going to be 2 times. So +9 -7, 2. So it is 2 into 10 to the power of 2. So volts. So it means otherwise you can write 200 volts. So second option is correct. Moving to question number 7. The capacitance of a parallel plate capacitor with air as medium is 6 microfarad. With the introduction of dielectric medium, the capacitance becomes 30 microfarad. So the permittivity of the medium is mentioned that epsilon naught. So this is absolute permittivity of free space. It is 8.85 into 10 to the power of -12 coulomb square Newton of inverse and meter square inverse. So first you write down C naught is equal to, directly you write down dielectric constant K is equal to C by C naught. So first let us find out the dielectric constant based on which you can find out the medium permittivity. So this is going to be K is equal to C is the capacitance of the parallel plate capacitor when medium is filled. It is 30 microfarad -6. When the space between the plates is filled with air, it is 6 microfarad. So this is going to be 5. So dielectric constant value is 5. So there is another definition, dielectric constant epsilon by epsilon naught. So this is also called as the relative permittivity. So therefore 5 is equal to epsilon by epsilon naught is 8.85 into 10 to the power of -12. If you multiply this, you'll get the answer as epsilon is equal to. So roughly this is going to be 8.85 into 5, 25. This is 40, 42, 4. This is again 40, 44. So 44.25 into 10 to the power of -12, remember. So you can make this as, so 0 by 100 if you want to make it, 0.44 into 10 to the power of -10. So unit is same, coulomb square, Newton square in Newton inverse and meter square inverse. So fourth option is correct. Question number 8. A dipole is placed in an electric field as shown. in which direction it will move. Remember, when in general electric field direction is always from positive charge to negative charge. So somewhere there is positive charge, somewhere there might be at infinite distance there is negative charge. So this is the direction of the field. So in order to increase the potential energy, so negative charge is in case moved towards negative. So therefore, due to which potential energy increases. So therefore, suppose I'll give you one more example. In Rutherford experiment, alpha particle, that is helium-224, moves towards the nucleus with a positive charge. So therefore, there is potential energy increases. So because there is natural repulsion. So this is the reason for the increase of potential energy. So therefore, this dipole with the negative charge moves towards the right in order to have potential energy move. So second option is correct. Now question number 9. Two charged spherical conductors of radii. So this is one of radii R1. This is the other with the radii R2. Connected by a wire. Then the ratio of surface charge densities of the spheres is. So as soon as this is connected by a wire, so there will be the same potential. There is no potential difference. It means that they maintain the same potential. So potential difference is 0. Remember, it doesn't mean that V1 is 0, V2 is 0. So V1 and V2 separately they exist. So get back potential due to a point charge 1 by 4 pi epsilon naught. It is Q1 by R1 is equal to 1 by 4 pi epsilon naught Q2 by R2. So charge is not the question. Charge density is the question. So get back the formula. Charge density, it is Q by A. Area of the sphere, it is 4 by R square. So therefore, let us substitute here. Q can be replaced with the sigma, first case sigma 1, 4 by R1 square divided by R1 is equal to sigma 2, 4 by R2 square divided by R2. So one R2 get cancelled, R1 get cancelled, 4 by straight away get cancelled. So therefore, sigma 1 by sigma 2. Sigma 1 by sigma 2 is equal to R2 by R1. So second option is correct. Question number 10. A parallel plate capacitor has a uniform electric field capital E in the space between the plates. The distance between the plates is D and the area of each plate is capital A. The energy stored in the capacitor, particularly energy stored per unit volume, we need to find out. So first get back energy stored. Expression of energy stored is CV square. So this is potential. So capacitance of the parallel plate capacitor is A epsilon naught by D. So get back the relation between potential difference and intensity of electric field, that is potential difference is equal to E into delta X. This is an example of dot product but with negative. Okay, so E is equal to delta V. So this is also called as potential gradient, delta V by delta X. So of course, this is an example of integration also. You can write dV is equal to minus E dot dx. So therefore, so simply for this particular situation, you treat delta V as V only. The gap between the plates of the capacitor is E. So therefore, E can be replaced with potential. Potential can be replaced with E into D. So now V square D square. So one D get cancelled. So therefore, half into A epsilon naught E square with the D. So this is energy stored. So which option is correct? Once you check. A into D is there, epsilon naught E square half. So third option is correct. So we'll continue explanation for the remaining questions in the next session. Thank you very much for watching my video, but don't forget to share and subscribe. So pass the information to your friends. Thank you very much.